So in the last class, we looked at transactions. What is the concept of a transaction? What are the properties that were of a transaction? And we looked at a couple of transactions that were consistent and some that were inconsistent. Okay. So today we will look at this in a little bit more depth, where we look at what we mean by a schedule and decide which schedules are allowed by the transaction monitor to execute. Okay. So a schedule is nothing but a sequential order of the instructions, and the instructions that we need to look at, or that the transaction monitor looks at, is basically the read, write, abort, and commit. Okay, but there are n transactions which can execute, but the ordering of the instructions of each transaction needs to be preserved. Okay, so a schedule can be looked at as a sequence that indicates the chronological order in which instructions of concurrent transactions are executed. Okay, so they are basically nothing but execution sequences. So we also said that if two or more transactions are executing, that is, if we call a transaction one as first transaction as T1 and second transaction as T2, then we can execute them serially. That is, T1 executes completely, followed by T2. But this does not give us any concurrency. So we don't really have such kind of schedules existing in our databases, because the scheduler or the transaction monitor also wants to improve performance of the database. Okay. So a serial schedule is a schedule that does not interleave the actions of different transactions. Okay. So it's like transactions executing concurrently. So each serial schedule consists of a sequence of instructions from various transactions, but the instructions belonging to one single transaction will appear together in that schedule. Okay. So if there are n such transactions executing in a serial manner, then if we remember our combinatorics, we would end up having n factorial different valid serial schedules. Okay. So if we have serial schedules, we have non-serial schedules also. So non-serial schedules are schedules where the operations from a set of concurrent transactions are interleaved. Okay. So if two transactions are running concurrently, the operating system may execute one transaction for a little while, then perform a context switch and execute some instructions from the second transactions for some time. Okay. And this switching can take place across multiple transactions. Okay. So the CPU time can be looked at as though it is shared among all these transactions. So with this scenario, we can have several execution sequences which are possible, since the various instructions from both transactions may now be interleaved. Okay. But not all such concurrent transactions result in a correct state. Okay. So what we just said is a schedule for a set of transactions must consist basically of all instructions of those transactions and must preserve the order in which the instructions appear in each individual transaction. But even if we do this, we could have concurrent transactions, some of which are not allowed because they result in inconsistency in the database. And we looked at an example prior where we said a schedule of this kind is acceptable. Because if you look at this schedule, transaction T1 would read A from what was already there in the database before any transaction made a modification. Same thing happens to B. Okay, it reads B from the database before anything modifies B, before any other transaction modifies B. Okay, whereas transaction T2 always reads the updated value of transaction T1. So it reads A from the updated value of T1, and it also reads B from the updated value of T1. Okay, so this looks at a consistent view of the database, and we saw that this was allowed and acceptable in the Dbms. So the transaction monitor would execute the schedule. Okay, but if we look at the second schedule, notice what is happening over here. Transaction T1 reads A from the database. So the value that was previously stored in the database is what transaction T1 will read. Okay, then T2 takes over. Okay, the operating system may have scheduled T2 to execute next. So T2 reads the updated value of T1, but when it comes to B, it is not reading the updated value of B. It is reading the previous value of B that was there in the database, because T1 has not yet updated B. Okay, so because of that, the view that it is having the values A and B would lead to an inconsistency in the final output. So such kind of transactions are not acceptable to execute by the transaction monitor. Okay, so we will see how this is handled by concurrency control. So not all concurrent executions basically result in a correct state. Okay, as we saw that some of them would be acceptable schedules and some of them running concurrently are not acceptable schedules. Okay, so if control of concurrent execution is left to the operating system, entirely to the operating system, basically, many possible schedules, including ones that leave the database in an inconsistent state, would be possible. Okay, so that is why all schedules have to be run through via the transaction monitor. So it is the job of the database to ensure that any schedule that is executed will always leave the database in a consistent state. So the concurrency control component of the database carries out this task. Okay, so it has to identify the schedules that guarantee consistency in the database. Okay, so we can ensure consistency of the database under concurrent execution by making sure that any schedule that is executed has the same effect as a schedule that could have occurred without any concurrent execution. Okay, in one sense, they are becoming equivalent to a serial schedule. We saw that this property is basically called the property of isolation. Okay, so where it gives you the feeling that you are executing in isolation, although there are concurrent executions in the background. Okay, let's look at some of the examples to understand which schedules are allowed and which are not allowed slightly better. Okay, in the first schedule, which we're calling schedule 1, basically transfers $50 from account A to account B, and then transfers 10% of the balance from account A to account B again. Okay, so there are two transactions, T1 and T2. T1 transferring $50 from A to B, and T2 transferring 10% of the balance from A to B. Okay, in this particular schedule 1, we have a serial schedule where transaction T1 executes completely and then transaction T2 starts executing. Okay, so in this schedule, we'll see whether we preserve consistency. Okay, so the sum of A plus B, if you look at the initial values of A and B, A is 1000 and B is 2000. The sum of A plus B before the start of the transaction is 3000. Okay, so we want to maintain the same amount after we do the transaction because we are transferring from account A to account B. So let's see what happens when we execute this transaction. Okay, so initially T1 reads A, so it will read A from the database. So that means it reads A as 1000. Okay, it modifies A by decrementing it by 50. So when it writes A now to the database, the value of A is 950. So when it then reads B, B is 2000. It modifies B by incrementing it, and then it writes B. So B now becomes 2050. Okay. Transaction T2 then takes over, but now notice that transaction T2 is in a after transaction T1 completes. So T2 will read the value of the transaction of T1's updated value. So T2 will read the updated value of T1, which is 950. Okay, it modifies A and then it writes A, so A becomes 855. Then it reads B. It reads B again after the write B of transaction T1. So it reads the updated value of B. So B is read as 2050. B is incremented by 0.1% of A, and then it writes B. So B becomes 2145. You can do these calculations and verify them for yourself. Okay. So the question that is raised is, does the schedule preserve consistency? So if we add this sum of A plus B over here, we still get 3000, right? So the sum of A plus B before the start of this transfer is 3000. After the transfer is done is also 3000. So we've not lost or created any money along the way. Okay. So this schedule preserves consistency. Okay. In this second example, which we're calling schedule 3, we are doing the same thing as what we did in Schedule 1. We're transferring 50 from account A to account B, and then we are transferring 0.1 of account A to account B. Okay, so we start off with the same initial values, and we need to see whether this concurrently executing transactions will be allowed in the database or not. Okay, now this one is different from the previous one, because in the previous schedule, T1 executed fully and then T2 took over. So there was a serial execution of T1 followed by T2. In this example, we are having the instructions of T1 and T2 being interleaved. And because they're interleaved, the transaction monitor needs to see whether this particular execution sequence will lead to consistency or inconsistency in the database. So let's look and see whether this is going to be a consistent or inconsistent schedule. Okay. So we start off with reading A. The initial value is 1000, and we modify A by 50, and then we write A. So this value of A becomes 950. Okay. Then transaction T2 takes over and it reads A. Now, if you look at this, transaction T2 is following the write of transaction T1. So it reads the amount that was written by transaction T1. So it reads A as 950. Okay. So then it modifies A again and it writes A, and it writes A to be 855. Okay. After that, transaction T1 takes over again, and here it is reading B. Okay, so it reads B as the initial value as 2000 because it is reading B from the database. It is not reading B of any updated value of T2. Okay, because T2 has not yet looked at B and T2 has not modified B. Okay, so it is reading B from the database because this is the chronological order that we are following again. Okay. So this is your chronological order that we go through when we're looking at the transaction. Okay. So here we're reading B. So B is read as 2000. It modifies B. Okay. And then it writes B as 2050. Okay. After that, transaction T2 takes over, and T2 now is doing a read of B. So it reads the updated value of transaction T1. Okay. So it is reading 2050. It then modifies B by adding temp to B. So whatever was the value of temp earlier, it adds on to B, and we get B to be 2145. Now, these were the exact same values that we had for A and B in our schedule 1 in the previous slide. Okay. So if we add the sum of A and B over here, we still get 3000, which is the same as what was there in the initial sum of A and B. The initial sum of A and B is 3000. And when we add these two values again, we get 3000. So we've not made money over here, nor have we lost any money. Okay, so there is a consistency in the transaction that is there. Okay, the sum of A plus B before the start of the transaction is the same as the sum of A plus B at the end of the transaction schedules, right? So this is a consistent transaction schedule. Okay. If we look at it, we'll realize that consistency is there because we had looked at a particularly acceptable schedule in the previous set of slides. And we said that consistency would be there if we read A in transaction T1 from the database, and then any further reads of A or B or any other value that it is reading comes from the database itself and not from any other transaction. So here we are reading all values of A from the initial database values itself and not any updated value of either A or B. So we are going to get consistency anyway. But nevertheless, it is good to check to see. So the sum of A plus B before the start of the schedule is the same as the sum of A plus B at the end of the schedule. Okay, so this is a consistent schedule and it is allowed in the database. Okay, so if we answer this question, does schedule 3 preserve consistency? Yes, schedule 3 preserves consistency. There's a further question. Is the schedule equivalent to schedule 1? Yes, it is equivalent to schedule 1 because in schedule 1, if you notice, the sums of A plus B over here were the same. So the final writes of the schedule A is 855 and B 2145. And the final writes of these are also 855 and 2145. Note that T2 writes A the last. Okay, so the last transaction that writes A in the schedule is T2, which is 855. And the last transaction that writes B in the schedule is 2145, which is the same as what happened in the previous one. So they are equivalent schedules. Okay. Let's look at the schedule 4, which is the third example that we're looking at. And the question asked is, should the schedule be allowed? Now, if you look at this, you do tend to see a couple of problems that are there in the database. Okay. And if you realize what the problems are, you will realize that in this particular schedule, the final write of A is not of T2, but the final write of A is of transaction T1. But the final write of B is of T2. So it's not really equivalent to a serial schedule. Okay, so that's why we end up having an inconsistency in the database. In the previous two examples that we looked at, the final writes that were coming into the database came from the same transaction. Whereas in this particular transaction, this particular schedule, one transaction is writing one value of as its final value, and the second transaction is writing one value, that is B, as its final value. So there is some kind of inconsistency in the database, and let's really prove it. Okay. So again, we start with the same initial values of A and B as 1000 and 2000. Okay. So when we read A becomes 1000. When we modify it, it becomes 950. Now T2 is again reading A. So although this instruction is coming after this particular instruction here, okay, this instruction is coming after this instruction because we go in chronological order, T1 has not yet written out the value of A. So which is the value that A reads? A reads it from the database. So the value of A again here is 1000. Okay. Then it modifies A and it writes A. So temp, when you calculate it, it is 100. So when it modifies A, it writes A as 900. And the final value written at this point of time of A on the database is A equals 900. T2 then reads B. Now, here it read A from the database. It's reading B also. B is also coming from the database, okay? Because transaction T1 has not yet updated B. So the B that is read is the initial value, which is 2000. Now transaction A takes over and writes whatever value it had of A, which is 950, okay? It reads B. The B that it reads now is from the database also, because transaction T2 has not yet updated B. So when it reads B, B is 2000. It updates B to 2050, and now it does a write of B. Okay, so it writes in the database B equals 2050. Transaction T2 takes over and it makes its modification of B. Okay, so that is 2100, and then it writes a B. So it has basically overwritten the value of B that was written by transaction T1. So it writes B and B becomes 2100. So notice here the values, the final values of A and B that are there on the database is A equals 950 and B equals 2100. So the sum of A plus B over here becomes 3050. Okay, if you add them up, you'll get 3050. So somewhere along the line, there is a mistake, and we have basically ended up getting $50 extra in our transactions, because A plus B at the start of a transaction is 3000 and A plus B at the end of the schedule becomes 3050. Okay, so I should have said A plus B at the start of the schedule was 3000 and A plus B at the end of the execution of the schedule is 3050. So somewhere there is an inconsistency that has been created in the database. And the inconsistency that has been created is because of the fact that some of these values were overwritten. If we had T2 followed by T1, okay, if we had this serial sequence, then what would have happened is we would have had the complete execution of T2 followed by transaction T1, and the writes that were there in the database would be the writes that were created by T1. So we would have got the values that were written by T1. So that would have been different values, and we would have got the sum that we required as 3000 again. Okay, so This is neither equivalent to T1 followed by T2. It is neither this nor it is equivalent to T1 followed by T2. Neither this set of transaction execution sequence. Okay, so it is not equivalent to any serial schedule. And we saw that there are problems. We saw that the final inconsistency was because we also ended up creating $50 from nowhere. Okay, the reason for it, as we said, is because some of the values were overwritten by another transaction. So to reiterate, the right of transaction T2 was overwritten by transaction T1, and the right of transaction T1 was overwritten by transaction T2. So the final outcomes were T1's right in the database, okay, for value A, and T2's right in the database for value B. Okay, so we have T1 doing a final write partially and T2 doing a final write partially. So a database is naturally going to be in an inconsistent state. Okay, so this transaction will not be allowed, this transaction schedule will not be allowed by the transaction monitor to execute because it knows that it will result in inconsistency in the database. Okay. So let's look at another schedule. In this particular schedule, we have, since this is a chronological order, we have instructions executing in this manner. Okay. So let's see what is our output. So T2 does a read of A. So it reads A as 1000. It modifies A, which we know as 100 now. Okay. And A becomes 900. It writes A. So the A written is 900. It then reads B. Okay, B is 2000. It modifies B 2100 and it writes B as 2100. Okay, so this is after the serial execution of T2. T1 takes over. It reads it as 900, modifies it. Okay, writes A as 850. It reads B 2100, writes B 2150, and then it writes B out. Okay, so if we add the values of A and B finally, it is 2150 plus 850. Okay, so we have to, if we add, check for a consistency, A is 850 and B is 2150. So the sum of A plus B at the start of the transaction schedule is the same as the sum of A plus B at the end of the schedule. Okay, so this schedule, it's a serial schedule. It is T2 followed by T1 and it leads to a consistent state. Okay. So let's answer this question. Are schedules 1 and 3 equivalent? So let's look at schedule 3. Schedule 3 was a previous example. So let's look at schedule 3. Okay, so this is schedule 1, which was followed T1 followed by T2. And this is schedule 3, which basically ended up giving us the same amounts that we have over here as 855 and 2145. So to answer the question, are schedules 1 and 3 equivalent? The answer is yes. Okay, so let's go back to the next question. The next question was, are schedules 1 and 2 equivalent? So this is schedule 2. Okay, so schedule 2 basically is T2 followed by T1. And we get values of A equals 850 and B equals 2150 for schedule 2. Okay, and in schedule 1, we had values of 855 and 2145. So although schedule 1 and schedule 2 are consistent, okay, schedule 1 is not equivalent to schedule 2 because the final writes of schedule 1 are written by T2, but the final writes of schedule 2 are written by T1, okay, and the values are different. So to answer this question, are schedules 1 and 2 equivalent? The answer is no. Okay. So just as a wrap up, each serial schedule consists of a sequence of instructions from various transactions where the instructions belonging to one single transaction appear together in that schedule. So that's what we looked at. So this becomes a serial schedule. Okay. So that's just to look at an example of a serial schedule. So only those schedules that are equivalent to serial schedules should be allowed to execute. So going back, we said this is equivalent to schedule 1 because it is the same. The final writes are written by T2. Okay. So the right of A, final right of A is written by T2, and the final right of B is also written by T2. So it is equivalent to this particular serial schedule. Okay, so that's why we had consistency in the database. So the transaction monitor only allows schedules that are equivalent to a serial schedule, okay, for execution in the database. Okay, so let's look at this one also. We looked at this one, schedule 4, right? And we said that this one is also an inconsistent schedule because it is not equivalent to a serial schedule. Okay, we cannot get T1 followed by T2, nor can we get T2 followed by T1. Okay, so in the next class, we'll look at the issue of serializability. That means we'll look at how we can look at a given schedule and find out whether we can get them into an equivalent serial schedule. Okay, so that's the idea about serializability. Okay.